Okay, the goal now is to be able to calculate limits without making a table. We want to find some algebraic methods to do this. So we got a lot of properties of limits that we're going to use. Essentially, it allows us to, to do algebra with limits and see how actually how easy it is. A lot of these rules seem pretty straightforward. We'll be able to prove them once we have a strict definition, and that won't happen to a little bit yet, actually, in calculus. So here we go. Here's some of the rules. Pretty straightforward, I think. The limit as x goes to a of a constant k is the constant. I mean, take a look at the graph, right? Here's an example. What's the limit of 2 as x goes to -1? Well, the function 2 just stays at 2. So the fact that x is going to -1 doesn't matter. The y value is always up there at 2. You can go anywhere you want. I could do the limit as x goes to 0. It's still 2. I could say the limit as x goes to 9. It's still 2. The y value of the function 2 is always 2. What does it care what x is doing? It doesn't. Let x go anywhere you want. You've got the limit is equal to the value 2 there, right? Limit of x rule, all right? What's the limit as x goes to a of x? That is, as x is getting close to a, what is x getting close to? Well, I'd say a. And sure enough, take a look at the graph here. Here's an example. The limit of x as x goes to 2 is 2, right? If I change this and say, no, let x go to, oops, let x go to 3, well, then x goes to 3. The input and the output are always the same. So whatever the input is getting close to, that's what the output is getting close to. Constant multiple rule. You scroll down to see this one. The limit of a constant times the function is the constant times the limit of the function. Do I have a picture here? No, I just got some calculations. So for instance, 2 times x is, I claim, 2 times the limit of x. So this 2 is multiplied by the x. I'm just going to pull it out in front and multiply it by the limit. This calculation we just did, the limit as x goes to 1 of x, is just 1. It's that right there. And so I've got 2 times 1, and the answer here is 2. Okay. Change this to anything I want. 6. This is now the limit as x goes to 6. So this limit is a 6, and you're multiplying that by 2, and the answer is 12. Okay. This rule actually isn't in the text. If you're looking at section 12.2, they don't have the constant multiple rule. They have another rule down below that I'll show you how they treat it the same way. Okay. So there's the constant multiple rule. I include it just because I think it's an important one. I know it's an important one for a lot of things. Here's the sum rule that says if you have the limit of a sum of 2 functions, that's the same as the sum of the limits. So really here I should have this in parentheses. Let me put it in parentheses to emphasize that I've got the limit of this sum is the sum of the limits. So take the limit individually and add the answers together, or add the functions together and then take the limit. Right? So let's see how that works. Here's the limit of x plus 2, and I'm claiming I can write it as the limit of 2 plus the limit of x. Now, pick a value of x you want to approach. I have here, I'm approaching x equals 1. So as x goes to 1, the line y equals x goes to 1. The constant 2 stays at 2, and so I should be getting the sum of those two, and the x plus 2 here is going to 3. Right? You can split it up. This is just, I mean, it seems pretty obvious that it should work this way, and it does. It's true. Sometimes obvious things aren't true, but in this case they are. One of the reasons why I put this constant multiple rule in here is that the constant multiple rule and the sum rule together should come up in a lot of different places, and anything that satisfies both of those properties is called a linear operator. Now an operator is like a function on functions. You put a function in, you get a function out. And when you take a linear algebra class, you're looking at linear operators. And there are things that satisfy these two properties. You've got the constant multiple rule, that is essentially you can multiply with a constant inside or a constant outside. And the sum rule almost looks like a distributive property. It almost looks like you're distributing the limit over that sum. You're not really distributing it like multiplying, but it has a similar effect. Right? So anyway, there's the sum rule. There's also a difference rule. The difference rule says that the limit of a difference of two functions is the difference of the limits. Again, I should have this in parentheses. So subtract the two functions first and then take the limit as x goes to a, or take the limit as x goes to a of each function individually and subtract the results. They're equal to each other. Okay. Here's an example. Right? The limit of 2 minus x is the limit of 2 minus the limit of x. I happen to be approaching x equals 1. And so I get that. I could change that to approach any number you want. Let's go to 7. If I can get it to do this. Come on now. There we go. Right, 2 minus 7 is negative 5. Product rule. Product rule is that the limit of a product of two functions is the product of the limit of those two functions. So you either multiply the functions first and then take the limit, or take the individual limits and then multiply by the result. It doesn't make any difference. Here's a little more complicated example. Here's two functions that we've already taken the limit of. If I multiply them together, that would be 4x. Well, anyway, it would be 4x minus 2x squared. Then take the limit as x goes to 3. I'm saying I can do each one individually. And I've already done each of those individually. This one is negative 1. This one is 6. And the result is negative 6. Notice you could just have plugged the 3 in to start with there and gotten the same answer. The constant multiple rule is not in the text because they use the product rule instead. Essentially, they're saying if this first function is just a constant, well, then the limit of a constant we've already established is just that constant. Okay, so they see the constant multiple rule as just a special case of the product rule, which it is. So I don't really need to list it, but I like to list it just because I think it's important. It's one that's used a lot. It's one that shows up in the theory of linear things. So anyway, then there's the quotient rule that says the limit of a quotient is the quotient of the limits. This is about as nice as you can go. You know, everything works the way you think it should work. There is one proviso here. If you're trying to divide by 0, if the limit of g here is 0, then this may not work. Right? Actually, this is going to be when it gets exciting. When there's actually a little bit of work to do is when that denominator is 0. Now, I want to look at a little bit more here before we move on. There's nice functions. If a function is a polynomial, an exponential, a log, a rational function, a trig function, a power function, essentially pretty much every function we've ever worked with in our lives here, then if the function exists at that point, then the limit as you go, so if f of a exists, then the limit as x goes to a of f of x is f of a. You can just plug it in. Essentially, if you look at the graphs of the functions that we've done, if you've got any spot where the function is defined, probably nearby points have nearby function values. Right? There's not usually breaks in the graph. If there is an asymptote, that's a spot where the function is not defined, so I'm not talking about that point. So if you've got nice functions, it's pretty easy to take the limits. Here's some examples. Here's 3 examples. So here's a polynomial function, x cubed minus 3x plus 3, and I want to take the limit as x goes to 2. Well, I do that by just plugging the 2 in. Essentially, all those properties that we had before tell us that this is okay, that this is the way it's going to work. Plug the 2 in. You got 2 cubed minus 3 times 2 plus 3, which is equal to 5. So the limit here is 5. Here's an exponential type function. The limit as x goes to 1. I'm just going to plug the 1 in. Nothing goes wrong. Right? The only time something goes wrong is when you try and divide by 0. Or you plug in a value that the function is not defined. Well, if you plug in a value where the function is not defined, well, then who knows what the limit's going to be. We're going to have to do some more work. That's what we're building up to. But if you're at a nice point, here's another example. The limit of the tangent of x as x goes to pi over 4. The tangent's got asymptotes at pi over 2 and minus pi over 2 and essentially all the odd pi over 2's. But pi over 4 is not one of those places. Pi over 4, the tangent's perfectly well defined. And nearby, it's perfectly well defined. And as the closer you get to pi over 2, the closer the tangent, the value of the tangent will get to the tangent. Sorry, I'm saying to pi over 2. The closer I get to pi over 4, the closer the value of the tangent will get to pi over 4. The tangent of pi over 4 is 1. So that one's 1. Okay. Next, I want to take a look at, in the next video, we're going to look at some limits that are not quite as easy to determine because you're going to be in a situation where you're trying to divide by 0. And we'll see how sometimes we can get answers